Welcome to the deep dive. So our mission today is to look a little bit past the individual headlines, the ones about climate change or pollution, and really try to understand the true connectivity of these crises. We're looking at how our collective, escalating human activity, everything from the garbage we throw out to the light we switch on, is creating these huge systemic threats.
Exactly, and they're accelerating.
Right. Faster than we can adapt.
That's the key. So we've pulled together some research that really maps out these pressure points, and you can see how they're all fundamentally linked. We're going to explore, I think, three major themes. First, the really shocking biological and chemical fallout from our global waste.
Okay.
Second, how we've introduced entirely new kind of subtle pollutants into the environment, like artificial light. And then finally, how all these localized pressures are pushing humanity right out of the stable climate niche we've occupied for thousands of years.
And triggering a surge in new diseases.
It all connects.
Let's start with waste then, because the numbers here, they're hard to ignore. We're talking about municipal solid waste, MSW. The world generated about 1.2 billion megagrams of it back in 2010. By 2025, that's projected to be 2.2 billion.
It's just that kind of growth is a staggering physical reality.
And it's not some abstract problem.
No, not at all. Our sources point out that 60 million people live within 10 kilometers of the world's 50 largest dump sites. And these dumps, they aren't just piles of trash. They're active chemical and biological systems. And they're dominated by this hazardous wastewater called leachate.
Leachate. That sounds like something straight out of a horror film. What exactly is it?
It's essentially the liquid consequence of decomposition.
Okay.
Yeah, it's often described as a dark brown, foul-smelling liquid that, accumulates at the bottom of a landfill.
And it's full of,
It's a toxic stew, heavy metals, various inorganic compounds, basically anything that can leach out of batteries, electronics, industrial scraps, everything we throw away.
Yeah. So it's a chemical hazard, for sure. But you said it's a biological problem, too, a ticking time bomb.
It is, because it's a perfect incubator. Leachate acts as a carrier for pathogenic microorganisms. It helps viruses move around.
Wow.
We've even seen recent evidence of this. Researchers detected fragments of SARS-CoV-2 RNA in landfill leachate.
Unbelievable.
But maybe the most insidious threat coming from these landfills is the acceleration of antibiotic resistance.
The silent pandemic, fueled by our garbage.
Yeah.
How does a landfill become such a primary driver for that?
Well, it acts as a major sink and source.
A sink and source. Explain that.
It's a sink because we dump everything there, right? Discarded pharmaceuticals, hygiene products, hospital waste, all these things introduce antibiotics and other chemical stressors like bisphenol A.
Right.
And that constant chemical pressure forces the bacteria in that environment to rapidly evolve resistance. So the landfill becomes a breeding ground, a source for antibiotic-resistant bacteria and the genes that create them.
That's terrifying. Do we have any numbers on how resistant these bacteria actually are?
We do, and it's pretty stark. There's a striking example from a study in Thailand. Researchers found that over 80% of the E. coli bacteria from landfill leachate were highly resistant to 4 common antibiotics.
80%.
80%, including things like tetracycline. That level of resistance in the runoff is a massive red flag for public health.
And then on top of this chemical and biological soup, we throw in microplastics. I always thought of plastic as more of a physical problem, for wildlife. But here, it's actually making the biological problem worse.
Precisely. It's an accelerant. Microplastics, which can be over 40% of the plastic we bury, they're far worse than just physical waste here. They're these tiny, high-surface area rafts for bacteria.
So like little condominiums for bacteria to meet up and trade genes.
That's a great way to put it. These surfaces are where genetic material gets exchanged really, really rapidly. The bacteria that colonize these plastics selectively enrich for those antibiotic resistance genes.
By how much?
By a lot. Sometimes it ratios up to 103 times higher than in the surrounding leachate. The microplastic is literally accelerating the spread of resistance.
That perfectly connects to our next topic, because pollution isn't just chemical sludge or plastic rafts. It can also be electromagnetic.
Right.
Let's shift from the sludge under our feet to the light above our heads. Artificial light at night, or Ellen.
And this requires a fundamental conceptual shift for a lot of us. We have to start treating Allen as a legitimate pollutant.
Like smoke or chemical runoff.
Exactly. It travels through the air, through water, and it disrupts biological systems.
We usually think of light in terms of brightness, but you can also think of it as a concentration of photons. So when we talk about wasted light, just how inefficient are we?
Staggeringly inefficient. I
Yeah.
mean, we sort of assume most outdoor light is useful, but it's not. In fact, less than one photon out of every 22 million reflected ones is actually captured by the eye of an average person standing just 10 meters away.
1 in 22 million.
Yes, so practically all of it is either pollution or it's just lost to space.
Yeah. And that pollution is growing fast. Satellite data shows the night sky is getting brighter, but the data from citizen scientists on the ground, that tells a different story.
A much more alarming story. The ground data suggests the rate of deterioration is much, much faster. Something like a 7 to 10% increase per year over the last decade.
So why the huge difference between the satellites and what people are seeing on the ground?
That difference is the hidden danger. It's the shift in the light spectrum. We've been replacing the old, warm, orange-ish sodium lamps with bright white LEDs.
The ones that are everywhere now.
Everywhere. And these white LEDs have a drastically increased blue light content.
And why is blue light in particular such a potent pollutant?
Because those short wavelengths, the blue, the violet, they are far more effective at interfering with biological processes.
In what way?
Well, they disrupt navigation in birds, feeding cycles in insects, hormone production in mammals, including us. We are changing the fundamental rhythm of the night with the color of our streetlights.
And then there's the rebound effect. So even though LEDs are more efficient, we don't end up saving energy.
No, we don't. It's a classic failure of resource management. Because the light is cheaper per lumen, we just use more of it.
Right? We light up things we never needed to light before. Bridges, building facades, empty parking lots.
Exactly. We end up with a net increase in energy use and light emitted, totally negating the benefit of the technology. We're sacrificing ecological dark for things that are purely ornamental.
So we've seen how these pollutants work invisibly in our trash and in our skies. But what happens when that industrial pressure gets really intense in one specific place? Let's look at a real-world case, the Mongla Export Processing Zone in Bangladesh, right next to the Sundarbans mangrove forest.
Mongla is a powerful and frankly scary example of how fast localized environmental collapse can happen. Before 2011, there was basically no industrial settlement there. By 2023, the sources show 129 industrial buildings, just breakneck speed.
A massive footprint in just over a decade. What does the remote sensing data say about the environmental cost?
The cost is extreme. Let's start with vegetation loss. The data shows that the dense vegetation in that area was completely gone by 2019.
Gone.
Gone. And forecasting models now predict that even the moderate vegetation will vanish by 2031.
You're basically taking a forest and turning it into a parking lot in 2 decades. And that has a direct human cost.
It does, a huge one. The Sundarbans ecosystem is critical for local ethnic groups. Honey collectors, loggers, their entire livelihood depends on that forest. When the vegetation goes, their way of life goes with it.
And the industrial activity creates a double whammy, right? It increases water demand, and at the same time, it increases the heat.
That's it. The surge in industrial demand created enormous strain on water. Drought-affected areas in the municipality shot up to over 30% by 2023.
And that's predicted to get worse.
Much worse. The prediction is about 60% by 2031, and this is compounded by the fact that they're paving over surface water bodies.
Which act as natural air conditioners.
Exactly. Water bodies minimize heat through evaporation. When you replace them with concrete and roads impervious surfaces, you lose that cooling effect.
And that brings us right to the urban heat island effect.
Yes. These impervious surfaces absorb massive amounts of solar radiation. The urban heat island effect has been growing consistently since 2011. The area facing high UHI that's over 2 degrees Celsius warmer than the surrounding countryside is predicted to hit 6.5% of the municipality by 2031.
So this shows how industrial growth doesn't just pollute. It fundamentally changes the local climate.
That changes everything.
Okay, we've established that waste, light, and localized heating are all accelerating problems. So now let's zoom all the way out to the biggest context, the evolutionary crisis and the historical niche that humanity has always lived in.
This is where we connect all those local impacts to the global human condition. It's really fascinating. For all of history, human populations have concentrated in this remarkably narrow climatic envelope.
We're climate specialists.
We really are. We thrive in areas with a mean annual temperature, MAT, around 11 to 15 degrees Celsius. That range has been the engine of human civilization for millennia.
It's hard to even wrap your head around that level of stability.
Yeah.
And now we're just rapidly vacating it.
Dramatically so. In the worst-case climate scenario, the average human is projected to experience a temperature shift in the next 50 years that's greater than the shift over the past 6 millennia.
6,000 years of stability gone in 50.
Gone in 50.
What does that actually mean for where people can live? What's the extreme consequence here?
The projection is just staggering. By 2070, 3.5 billion people, that's about 30% of the projected global population, are expected to be exposed to an average temperature of 29 degrees Celsius or higher.
And to give you some context for that,
For context, conditions that hot are currently found on only 0.8% of the Earth's land surface, mostly the Sahara Desert.
we're pushing billions of people into climate conditions that just don't support civilization as we know it.
Pretty.
And our sources link this massive destabilization directly to the rise of new diseases, which is explained through something called the Stockholm paradigm.
Yes, the Stockholm paradigm, or SP, is a powerful framework. It argues that the rising rate of emerging infectious diseases, EIDs, isn't just bad luck.
It's not random.
It's not random at all. It's a unified systemic consequence of hyperurbanization, climate change, overpopulation, all the ways we're distorting the biosphere.
And this framework helps resolve what used to be called the parasite paradox, right? The old idea was that parasites and hosts needed these long periods to co-evolve before a jump could happen.
Exactly. The SP suggests that when we accelerate climate change and ecosystem destruction, we create what researchers call a sloppy fitness space.
A sloppy fitness space.
Think of it this way. You just destroy an ecosystem, you stress out the animal populations. The existing parasites, which make up about 60% of all species, suddenly lose their hosts. They have to rapidly switch or generalize, potentially in just days or weeks. And they look for the next available, most numerous host species in that messed up area.
Which is almost always us, Homo sapiens.
Which is almost always us.
So we destroy the environment, creating chaos, and that chaos weaponizes the most numerous life forms, the parasites, against us by forcing them to find a new home.
It's the ultimate feedback loop. The speed of this host switching explains why we're seeing all these novel EIs that have no long evolutionary history with humans. We've created the conditions for a disease explosion.
And given that conclusion, the Stockholm paradigm also proposes an ethical framework, the laws of biotics.
Yes, and they're quite stark. They basically set the boundary conditions for our survival. The first two laws are absolute. Humans may not harm the biosphere, and humans may not injure any portion of the biosphere through action or inaction.
And the third?
The third law allows for exploitation, but only up to the limits that don't violate the first two. It's a powerful statement that we have to put the health of the biosphere first.
And clearly, we are violating those laws on a massive accelerated scale, on every single front we've discussed today. So what's the core takeaway here for you, the listener? We've connected the dots between these threats that seem so separate. The speed of change is really the unifying factor here.
It is the speed and the connectivity. The research shows that the generalization of parasites, that quick host switching, may happen at rates 100 or even 1,000 times faster than specialization, which is the process that would eventually exclude humans from their host range.
So the threat is evolving much faster than the solution.
Much, much faster. This research suggests that even if we achieve strict climate mitigation today, it will take 150 to 250 years just to stabilize the new disease landscape we've already created.
Wow.
The harm accelerates the evolutionary threats much faster than we can manage. And this raises a really important question for you to consider. If the environmental harm we've caused accelerates evolutionary threats much faster than we can manage or adapt, what level of ecological buffer must we build into our current systems just to survive the next 2 centuries?